of dark matter. Let me see. Where is that? Yeah. So can you see the screen? Yes. So if you look into the video, you will see that if you zoom in into the universe, this is a little bit similar to what cosmic microwave background. There it was blue-green, here it is red dot. So now let us see what, if you zoom in, this is a homogeneous universe from very far distance. That's why we treat this whole thing is dark matter basically, filled with universe, but galaxies are like dots here, not even dots. So you can think of this whole thing as water we are seeing, but if you take a microscope, then see what happens. So this is the microscope, means like we are zooming in. Okay, so if you zoom in, so then you will see what happens. So we are now slowly coming to a smaller distance, 500 megaparsec. You see the intergalactic galaxy is 1 kiloparsec. So we are still now 250 megaparsec. So you are seeing these structures. This the yellow one is the more dense dark matter. Basically, there is no luminous matter here. It is just a visualization of dark matter. So wherever you see more yellow, that means there is more dark matter there. And filaments, all are dark matter. So if you see human brain's picture with neuron, you will see they look exactly like same. And sometimes you will see the knots of the neuron where more neuron meets, it exactly looks like that. So if you see the dark matter distribution and simulation, and our human neural network brain is very close, similar. So one day I also could not differentiate which one is what. So now we are coming even closer, zooming in, 100 megaparsec. So it is the size of a galaxy cluster, you can see. Now 60 megaparsec. So these dots are huge number of galaxy inside, okay? Because galaxy size is kiloparsec, okay? Now still we are in megaparsec, 1,000 times more distance than galaxy diameter. So now you are zooming in, now you are looking into one cluster of galaxies. Say this green one is a cluster of galaxies. More galaxies there inside. It's a megaparsec size. And then as you zoom in more, 3 megaparsec, then you are slowly moving into this simulation. Now they will again zoom out and go back. So you can see all these things, different length scale, there is dark matter. It's not only just in one scale. We started with 500 megaparsec. Everywhere there is dark matter. This spot, yellow lines are basically dark matter. Okay. So now, if you actually ask that how all this dark matter, because in the beginning it was just inflation, nothing, and then there is a tiny perturbation of 10 to the power minus 5. And then from there, how come all these deep structures of dark matter are produced? So that is called cosmological n-body simulation. Means we put, I'll share this. We put this delta rho by rho 10 to the power minus 5 from inflation, or in other words, quantum mechanics origin. And then these fluctuations, we know that we expand it in different Fourier mode, and they are called delta K. So different Fourier mode basically is a linear combination of splitting this function. This is in the position x in physical space. Then we are going into the Fourier space, and this delta K is the growth of perturbation in different length scale. We can, like we can split delta function in sign harmonics in mathematical physics. Like that, this is like you can think of a delta function as we show you on one video. And these delta functions are in many places. But the amplitude of the delta function is very less, 10 to the minus 5. But on an average, these peaks are there above a mean density. And that mean density is very high, but fluctuation is only 10 to the minus 5. But this 10 to the minus 5, when they enter the horizon, we remember that how the H inverse is the horizon. They enter the horizon, more and more modes, different Ki, delta Ki, enters the horizon in radiation dominated universe and in matter dominated universe. You remember, all of you, that they enter the horizon and start growing? We have told you that when they entered, because the H inverse we have plotted, different scale we have plotted. Okay? Yes? You are able to hear?
Yes, sir.
Yes or no? Yes? Yeah.
Yes, sir.
So once they enter inside the Hubble horizon, then there is an equation that we are not doing, that is cosmological perturbation equation. Generally, you need Euler equation, and Poisson equation. These two equations you can solve. We are not, this is another 5-6 lectures. Those who want to know, that is the second level of cosmology. What does it do? It basically gives you an equation of delta double dot plus something. It is not exactly what I am writing, plus some omega matter, function of omega matter enters is 0. So it tells you how delta grow, delta as a function of time. So delta means basically delta rho by rho. In my new definition, delta means delta rho by rho. So delta t starts with, if we plot, we'll see that delta t starts with a very small value, 10 to the power minus 5. But then it grows. It grows and there is a function. So we'll see that if you ever do the second cosmology course. But it grows, or it may grow like this, depending on different dominant. But actually it grows. So now what happens when delta t starts growing, then suppose this is delta t. If it grows, then it will collect more matter here. And the vacuum in between will become more and more vacuum. So void becomes more void and the structures start pulling more because it has more gravity. So that's what we are going to see now in a simulation. Simulation does not solve this mathematical equation. Simulations, by solving these mathematical equations and with some nonlinear physics, that is called analytical calculation, analytical. But what simulation does is very simple. You say, like, okay, this is my box. They choose a box size, say megaparsec or 100 megaparsec, depending on the. Simulation means it actually is a huge simulation because you are trying to reproduce universe. So sometimes they are like 5,000 CPU, high processive CPU runs for 2 months. Okay, so then it's called supercomputing. In AI also we do it, but not in that very high range, supercomputing. And you choose some random fluctuations in the beginning of the order of 10 to the power minus 5. And then you evolve it with the, give the gravity between them, because gravity is the only force and the universe is also expanding. You put that. There is a way to do that. We are not going. And then you run the supercomputing and you see whether at present time, whether you can produce that filamentary structure. And you can produce the galaxy clusters as well as inside dot, you can produce the galaxy. And it will be amazing to know that even with this simulation, we are able to even locate our Milky Way galaxy also, that it has been formed after 8 billion years or something like that. So it's a very super high, costly supercomputing simulation. It costs a lot of financial resources, But nowadays the code is actually public. So if some university has the resources, it's for cluster computing, you can run the code by downloading it. It's called Gadget or Millennium simulation. And so what we are going to do now, I'm going to share with you a simulation which, are you able to see the screen? Yes?
Yes, sir.
So see how the simulation is done. It's a visualization. Filaments in a massive web, like a brain. So you start. Oh, this is the same one. No, I think this will show you at the end. There is a video at the end. So I want to show the box. So now you see we are zooming in. Now, as the we'll run the movie where it is in the time. Now it is going in the evolves, because we want to see it from time now, because previous one was in space, means at today's time we were zooming in at different distance in the space, but now we will see how universe evolved from what I was telling, primordial roughness. Primordial roughness means 10 to the power minus 5, and that is a blessing, because if we were not coming from quantum mechanics, you will not get that tiny fluctuation, and a homogeneous, pure homogeneous universe can never create galaxy. So let's see. So this is the beginning, and you can see the redshift is running on the top left. So redshifts at higher redshift mean earlier time, okay? So we run with the redshift of 10 or 12. 10 redshift 10s means it is almost 10 billion years back. You can check it. That was actually homework. You can even Google search what is the time and redshift. They are mapping to one another. Okay, we have done it for time with scale factor, but redshift and scale factor is also connected. So redshift Z means is very early universe, but of course after CMB, because during CMB there was no atoms. Also atoms form after at CMB. That is Z is equal to 1000 or 1100. So from 11,000 to 10, redshift 10 was preparation, and from 10 actually to till today, the galaxy is forming. Okay, so let's see. You will see the redshift running on the top. So blue one is void. Void becoming more void. You can see filament. Then how the filament structure comes. Now redshift 3, 2, 1. Today is basically 0, you know. The more and more structures are going, 0.1. And all these filaments are made up of cold dark matter. And these are the real survey on the left side by SDSS, slow and digital survey, and right side is the scale. Okay. So now you see all the things you saw here is basically nothing but dark matter. Is it clear now that how starting from 10 to the power minus 5, you put it in a supercomputer and you see that how the filament grows, and you can even point down our Milky Way today. So this is amazing that we are actually able to understand. And for all these things, now I am going into the mathematics. What is needed is basically these simulations are about matter, no? Matter, galaxy is forming, but actually 26% is dark matter and 4% is baryon. ठीक है? 4%. But as we know, these baryons means proton, neutron, and electron in cosmological sense. They are called baryon. They were interacting with photon till Z is equal to 1100. That is CMB. So if they are interacting with photon, and photon has pressure, as we know. So outward pressure photon. So that's why baryon photon fluid also has outgoing pressure. So they are not able to clump so much. So that's why the dark matter actually started clumping. Out of that dark matter is this one. Dark matter started clumping much before. So their growth delta as a function of t, actually it was going little bit oscillations, and then it starts growing faster. Okay. Whereas baryons were much lower. They were oscillating because of the photon connection, and then slowly they tried to rise up when this decoupling happens. Means when basically CMB. Basically, when the baryon and photon decouple at CMB, means atom forms and light peak started. That means photon does not interact with it anymore. That time onwards, the atoms starts falling, but falling where? In atoms start falling or following, both are okay. Following gravitational potential well of dark matter. Because dark matter was already going high up, that means it has already created more structure and more void. And where there is more structure, suppose there is a more structure here and more void, so there are already clump. So that means here you have a deeper potential well of V phi. So then it will attract the baryons there more. So how the structure form in the universe is actually visible matter. Now we see the galaxies, but actually dark matter first created the potential well at different place, and then baryons just fall on it. And dark matter potential is also very powerful because it is 26% of the universe. Is it clear? Hello? Any question? Hello? Yeah.
Yes, sir.
Huh?
No, sir.
Yeah, it is understandable, no?
Yes.
First, dark matter creates the potential well, the high gravity zone, and then baryons follow it. So that's why today, if we don't see the dark matter directly because it does not interact with anything. But if we locate the baryons or the visible matter in the universe, then you know that there is a surrounding dark matter. And there is a mapping that has been proved. I'll not go into the detail, but the main idea of now I'm moving to galaxies. Suppose you locate a galaxy, for example, say Andromeda or Milky Way. Andromeda galaxy. So now you will see it is like a two-dimensional thing, but it's like a very thickness is much less than the diameter, but the dark matter is actually like a sphere, as we already told before. Dark matter is like a cloud. Okay. It's like a sphere. We don't see them, dark matter, directly, but there are many ways to detect them indirectly. So this is the galaxy, it's like an egg and its nucleus. So this is the galaxy and this is the dark matter. These are called DM halo. We have talked about it before, and this is the galaxy. So this one is actually 3D, means sphere. This one is like a disk. Galaxies are more like a disk. And it has shown that without this 3D halo, you cannot make this Milky Way or Andromeda-like galaxy stable. So if you are having a stability of light or galaxy inside because of the dark matter, makes galaxy stable. And we know that how they clump. This is also verified from simulation. So in simulation, it is you will see that it's a 3D box simulation. There, each dot is basically a sphere, basically, because we are zooming in from a very large scale. So when I was showing you the simulation, at the end, the blue line dot, and you see the filaments are inside, but each dot is nothing but a spherical halo here, and it is containing a galaxy, or it can be a galaxy cluster if you go to a bigger scale. So don't think that dots are like particle here. We are now looking at a megaparsec scale. So where even galaxy looks like a dot, and galaxy cluster will look like this. So that's why each yellow dot is like a sphere of this dark matter halo. And if you zoom in here, zoom in with a very high resolution simulation, then actually you see the production of the halo of a sphere through n-body simulation. And how do we verify it that it is there? That is using the Newton's law. Newton's law. You know that the motion of the stars in the galaxy depends on the potential well or the gravitational mass inside, and there is huge mass of dark matter. So this is the detection of dark matter, first detection by Vera Rubin, I forgot how to spell, but Vera Rubin. There is a telescope on her name going on. She first detected the dark matter. How? No, she plot the rotation curve of galaxy. So velocity as a function of r. So you know that. Now forget about the 2D structure. Just focus on this galaxy. So now you know that they are all rotating, the stars and the thing. And Rubin wanted to measure the velocity of speed, and the velocity nahi hai, speed kind of. It's now not giving a direction, radial velocity or radial speed as a function of distance. So now I'll give you take your pen and paper. I'll give you a class 12 mathematics. Suppose for simplicity, assume that the galaxy has a uniform density. Rho is the uniform density. It is not, but rho uniform. So rho is a constant of matter. So now, if you calculate the velocity, this is the center of the galaxy, and this is the rotation of the stars or hydrogen cloud. I'm planning to make it here. So take a unit mass here, m of unit mass. So what is happening? How do you calculate the velocity using using class 12 mathematics? Who can be inside? There is some mass, uniform density rho, and that is the distance r. There is no nothing special here, just the center of the galaxy. So what is the force balancing? Who can tell me?
Gravitational to centrifugal.
So G m inside, whatever the mass, times the mass of the particle, test mass, by r square, that is the force, is equal to m times, who can tell? What is the centrifugal force? R, very nice. Now this m inside, what is the m inside as a function of r given a uniform density? Who can tell me? This is also a function of r and rho. What is the
4/3 pi r cube rho.
Okay, so G rho 4/3 pi r cube. Yes, this is the volume times the uniform density by r square. M gets cancelled, v square by r. So how much is the v? Can somebody tell me?
So if it's galaxy, then it will be a disk, right? Not a volume. So 4/3 r cube is for spherical distribution, right? If we consider a galaxy, then
yes. So that's the approximation. If you take instead of disk, if you take little bit because that's what we am coming. That most of the matter you will see now. Just hold on now. I'll give you the answer. Okay. Okay.
Okay.
So V is how much? So if you do instead of a disk, for the disk, this calculation will get little correction. Okay, we are assuming like a uniform density sphere, isn't it? Yes. Okay. But if you just even calculate it like a disk, like a sphere, then what will be the answer? Who can tell me as a function of R? Just use this. I have done everything for you. V will go as no. I just want as a function of R, the functional form. R to the power. So square root of R. Yes? Right?
Yes.
So it will be square root of R. So if you plot V square, it will be like a linear function of R. It will increase as you go away from the galaxy. The further you go, it will increase. Now, suppose the galaxy ends here. That is the distance, that is the radius of the galaxy, say R0. After that, how it will go? Use the same formula, same concept, balance it, and tell me the functional form of how it goes. Do it now with the pen and paper. So I'm talking at a distance which is away from the radius of the galaxy. Okay. Got it?
Go as 1 by root over.
1 by?
Root over R.
V square.
So V square will go as 1 by R.
V square will go as 1 by R. So it will fall like 1 by R, V square, if I plot. Yes?
Yes.
So everybody got it? Because this term 4 pi 3 pi R cube times rho, this will not depend on R anymore, because even if you go away from the galaxy, what matters is the mass enclosed by the galaxy, m. So m is a constant number, 4/3 pi R cube rho. So if you are inside, it is a function of R. You are getting more and more mass, center of mass. But if you are outside the galaxy, you are not picking up any mass. Okay. Is it clear for everybody? Yes?
Yes, sir.
Now, once we actually see from observation, then we see that actually it is not falling. Vera Rubin find out that it is actually flattened out. Actually, he plotted V. So then it will be like a square root of R, increasing square root of R, and then it falls like 1 by square root of R. So now, if it is not falling off, that means the only option, if it is not falling off, that there is hidden mass, which we don't see. Because we know this rho is basically nothing but the visible rho we are talking about, 4/3 pi R cube, approximately. So there must be hidden mass And not only that, that hidden mass extends farther from the edge of the galaxy. So edge of the galaxy is 1 kilo per second, it can go up to 10 kilo per second. So that's what, then people started thinking that what is that hidden mass, how to match that. Then they exactly did calculation with the disk, as some of you have already asked. Then you can do the mathematical solution. And they found that actually the dark matter, there is extra matter with the density rho dm, and the density they found has a profile is called NFW profile. Density is not a constant density, but more or less it goes like this as you go away. But nowadays people find that NFW profile is wrong. Actually, the density is constant near the center of the galaxy. So it's basically flat, and it's uniform density up to half of the radius of the galaxy, or like 1/5 of the radius, and then slowly falls off. So that is the dark matter density, and it goes off farther away from the edge of the galaxy, from the radius R0. So the picture is now, this is the visible part like a disk, but it goes 10 times than the distance of the visible galaxy, and it is like a sphere. So this is the mapping, and the density of that sphere falls like this. In the beginning, it is constant near the galaxy, and then the density falls like this. It's like a r to the power some factor, r to the power -1, or I forgot. It is called NFW profile. It's a very famous work. They theoretically calculated. But nowadays, there is a problem that NFW profile is calculated and was supposed to match, but we found that actually it is not matching. It is flattened, constant density. And NFW actually told that it will be like a rise up towards the center. Rise up means it is called cusp nature. But what we get is called core nature. Core means it's kind of equilibrate and same density. Okay. This problem is called core cusp problem. I will tell you a little later today. This is a huge problem with dark matter. I'll tell you why. So now this is the dark matter. Now if we see the dark matter halo, 3D halo in more detail, then this is your Milky Way. Then you'll see there is some galaxy, small galaxy, chota, like satellite, like we have moon is our satellite. Today is Buddha Purnima, moon, full moon, and also today is Chandragrahan. So these satellites are called dwarf galaxies. Okay. Now for our Milky Way, if you look at that n-body simulation result, which maps the universe pretty well, it predicts 200 such satellite galaxies, 200 to more, even 500. I don't know the number, but depending on the nature, okay, 200 to 500 dwarf galaxies predicts. But what we we have observed around 50. So around 510 times are missing. So why they are not seen? This is called another problem called missing satellite problem. Missing satellite means not satellite. Okay, spelling is wrong. Satellite galaxy problem. Missing satellite problem. They are the satellite galaxies. Now, what this millennium simulation or n-body simulation does, that is our nature. That dark matter is cold WIMP, weakly interactive massive particle. And there is a model I was telling you, the mass is of the dark matter. We guessed it will be 100 GeV. They are like 100 times the mass of it. They are called supersymmetric WIMP particle. They are the most studied and most expected dark matter candidate. And their production has been the same way I was telling you. This chi comes in the early universe and goes into standard model particle. And then first 3-phase step. First, both sides equal, then chi started vanishing, then freeze out happened, and then the dark matter number density chi falls, and then co-moving density becomes constant. This is like the rho chi today. Remember this three-stage process?
Yes, sir.
So now, why we were looking for this 100 GeV? Because you tell me, I was discussing this before, this false off happens because the dark matter was at some point, what it was doing? Tell me. It was, this exponential fall happens at some point. Why? You all forgot. Why the number density of dark matter was going down? Anybody remember?
The annihilation process.
Because this part continue, but this part stops because there is not enough momentum. You remember? They are light particles. Yes?
Yes, sir.
So I can clearly see that you have forgotten many things, but you have to read it, the notes and video recording. Then only you will be able to answer the exam question. Because a lot of things we covered, though we covered in 10 class simple mathematics, but quite a new concept, okay? You have to read it again. So this false off happens. So now you tell me, this false off gamma was, I told you one day, it is n times sigma times v. And this v is basically 1, very high velocity, so n times sigma. It has to be equal to what? When the false off when the freeze out happens, who takes over this gamma rate? Freeze out? Who can tell me?
Hubble expansion.
Yes, very nice. Hubble's expansion rate. Because it's the expansion which dilutes the density so that they don't annihilate each other. There is a competition. Clear? We did all these things again 2-3 times, okay? So now you tell me if sigma is high for a particle, dark matter particle, then we get today lower dark matter density, higher dark matter density, or it will freeze out later. Which one will happen? You just tell me. If I increase sigma, the rho dark matter today will decrease or increase today. Suppose some dark matter candidate has heavy way heavy or way more annihilation rate. Then we end up in a less dark matter density today or more dark matter density. It's a common question, common sense question from here. So if sigma is high, then freeze out will happen earlier or later?
Later.
Why? I have told you. No? Sigma means what? Interaction rate. So if somebody is interacting heavily with a high sound, then you have to really separate them far away so that they don't hear each other, isn't it?
Yes, sir.
That means Hubble has to really, the expansion has to be even more and more farther. That means later they will be able to compensate this sigma. But if sigma is lower, then Hubble will win earlier. So lower sigma means you are actually ending up in a high density today because you will get freeze out earlier. And higher sigma means you will end up in a lower density today. Is it clear? Freeze out density. Very nice. So now you can map rho chi today with exactly with the sigma. Sigma, that is the particle physics. Given a sigma, you will find what is the rho today. And now, for some physics of Higgs boson, they are called weak scale physics, there is some sort of sigma which goes as Higgs boson's kind of weak scale coupling by d square by the mass of the particle square, m square, something like that. Okay, you don't need to know that. But they calculate their sigma all the time in Switzerland CERN collider. because Higgs boson physics is being discovered there. Okay, so they calculate and they find a value of sigma naught, and they also have some particle called WIMP particle in their Higgs theory. It's called WIMP particle in supersymmetry theory, SUSY Higgs theory. You don't need to know. It's related to Switzerland CERN particle physics. So they have some particle called weakly interactive massive particle. They are the super partner of some particle. You don't need to know. They are called chi. And they have an interaction cross-section sigma naught. Then they calculate. And given the sigma naught, they put it in this plot and they found a corresponding rho x, because there is a one-to-one mapping I just told. Is it correct?
Yes, sir.
Higher sigma means low rho, lower sigma means high rho today. That means if you fix sigma, if you will also fix the line dot rho also. Correct?
Yes, sir.
Once they fix, they have their sigma calculated from their particle physics experiment, and they found a corresponding rho naught, which magically coincide with the rho dm not observed today. They were not looking for balancing, giving you dark matter. They were doing some Higgs physics. So they found a sigma and with some chi particle, which has the property of dark matter. Then they calculate from this guy and they say, hey, I'm getting exactly rho naught x, which matches the observed dark matter density from galaxy rotation curve. That means maybe nature is hinting that these chi particles are our dark matter, which are produced like this in the early universe. This production mechanism called WIMP, WIMP freeze out, which I have just taken. And how to detect them? I am coming to that next. But as you were not looking to get the dark matter density from Higgs, but as a byproduct it matched, then people thought, wow, maybe nature is giving us hint, because we are looking for Higgs boson, but we also got a candidate which exactly matched with dark matter density. Then for last 30 years, almost 20 experiments started building up to detect this WIMP dark matter, and how they detect, that will be I'm discussing in the next 10 minutes. So is it clear now? So what is this property of the WIMP? I'll just, even if you don't know the property that much, I'll just tell you that the property is, number one, they're very heavy. Cold, heavy or cold means they're non-relativistic. Cold means non-relativistic. Because their mass is much higher than the mass of the proton, 100 GeV. So they became non-relativistic at very early time, number one. Number two, chargeless. Dark matter cannot be charged, because if they have charge, then they will have interact with light photon, and we have detected them. Number three, they are stable over billions of years. If they decay into some other particle, then you cannot do that. Okay. And number four, they interact with gravity for sure, but they may interact with weak interaction. This we don't know. But if WIMP is a dark matter, then it should have weak interaction. So that's what the next slide is. The next slide means not slide. So detecting dark matter. Detecting DM. So now we know all these things. When we are planning to detect DM, why we want to detect DM? Because we have seen them like black hole. We cannot see black hole. We can feel their presence through many things nearby. Like that, dark matter was the presence of dark matter. Presence of dark matter is only through gravity. So one presence we have seen through rotation curve. That we need, there is missing matter. There is another one called weak lensing. Weak lensing is what? So suppose you have a cluster of dark matter, as we have seen today from Millennium simulation, and you are looking at your cluster of dark matter, and there is a star here, or not star, say there is a galaxy, and then you are here observing. Your eyes in here, telescope. Then what happens? Because of this, in between there is a cluster of dark matter, the light will bend and light may come in a different distorted way to us. So when you see the image, you will see instead of a proper elliptical galaxy, sometimes they get distorted. They get distorted, and that and you can even get multiple copies of the image. They are called strong lensing. And if they're distorted little bit, their ellipticity changes, then they are called weak lensing. And people know that how much dark matter can distort you exactly by computing simulation. So given the nature of the shape of the images, they can map back the dark matter. And this is called weak lensing. And they also have found a similar dark matter profile, what I was telling about rotation curve. And then C is CMB. We have told you before that CMB peaks are depending on dark matter, because dark matter, we have shown you in a video that dark matter started clumping during CMB also. So they change depending on the peak of the CMB. There are many ways we can calculate the dark matter density. So there are many ways we have found that dark matter exist, but we don't know what it is. What is their nature? What particle they are made up of? How they are there? We have no idea. We don't know. Still, it's a complete mystery. Any day people discover it, it will be Nobel Prize that year. Because it is 26% of the matter, and where we have 4% of the matter is all these galaxies, all these electrodynamics, all the physics you are doing, all astronomy, all class 12, BSc, MSc physics is all about 4%, but 26% is unknown. Like the dark energy also, 70%. We know that exists, but we don't know what it is. Clear till now?
Yes.
So now detect WIMP. So why WIMP? Detect WIMP. So first of all, detecting DM needs guesswork. What is guesswork? That what is their interaction with us, with the visible. Now there are two choices. One is both they can only interact with gravity. Another is gravity to high, because without that you cannot see them, plus weak interaction. This is allowed. Strong interactions and electromagnetic interaction is not allowed for dark matter. Then we have detected it already. So this is a very bad situation, because you will never know what dark matter is. You will only feel their gravity. But if this is the right one, then nature is kind to us. If this is the case, then nature is kind to us. And that's the hope people started building this WIMP. And WIMP dark matter, as I told you, maybe people thought that from CERN or Switzerland particle physics, the hint or the coincidence, sometimes my writing not good, coincidence of rho naught, I just said you, that they were not looking for that rho naught X, they were looking for Higgs physics, but they got luckily an amazing coincidence that, hey, with the same thing what Higgs physics is giving, I am getting a dark matter particle with exact number density people need cosmology. And this is called, they call it WIMP miracle. Why it is a miracle? Because you were looking for something else, but you got a gift. Right? So then the whole scientist from 1990 say started looking for this WIMP miracle. The WIMP miracle means what? You assume that the guesswork is this dark matter is WIMP, and it interacts with us. So this is the dark matter, chi. As I told you, it can interact with the standard model particle through weak interaction like electron, positron, or it can interact with quark and antiquark. These are all given in the Switzerland thing. So these are all still an assumption that under WIMP. If you believe it is WIMP, then they interact, we know. But whether WIMP is dark matter or not, it is an assumption. And if we build experiment, we have built, and if we detect it, then that means the assumption is right and there is Nobel Prize immediately. So how they built the experiment? So this is Earth and this is mountain. Mountains are much bigger than tree, but you have to see it. So, and our Earth is part of the Milky Way, rotating Milky Way. But I'll not go into the detail that it is shown that this halo, DM halo, has very less angular momentum, so it does not rotate. Or rotate very slowly, will not go. It is also truth from N-body simulation, they also find it. So now if you are rotating and if the dark matter clouds are kind of fixed and you are going with a huge speed, you know the sun is, our solar system is going in the galaxy. Anybody know what is the speed? Who can know? Who can tell me what is the speed of our galaxy? Rotating, moving into the Milky Way. Anybody has any idea? It is around V equals to 200 kilometer per second, much faster than the jet plane. Okay, very high speed. Our solar system is moving in the galaxy. There are billions of such suns in our galaxy. So, what will be the velocity of dark matter cloud you will experience by normal relative motion? Anybody can tell me? If you are going in a train and the trees are not moving, but what is the velocity you see? The trees are going backward. What is the velocity?
That be our velocity.
Simple question. Please speak, no? So if you are moving in the galaxy with a 200 kilometer per second, your local velocity, then you will see the cloud of dark matter, DM cloud is hitting us in the same speed, right?
Yes, sir.
Now, the DM does not, there are things like that. Now, how to detect dark matter? Because dark matter has to interact. If it does not interact, how can you detect, right? Yes? So, DM can interact with nucleus. Because neutron and proton have weak interaction, right? Yes? So, dark matter can come and hit a nucleus and scattered off chi particle, and the nucleus will recoil. You should read it. I cannot tell you all the thing. It is called recoiling of nucleus, called WIMP detection. Now, there are many other things can hit nucleus. There is cosmic rays, high energy neutrinos, and all these things. Electrons can hit nucleus, muon, tau particle. But all these charged particles get screened on the Earth or in the atmosphere. They only just vanish because of the interaction. Dark matter and another thing, neutrino. down or 2 kilometers down the ground in a mines, coal mine or any mine, they made the detector. So they made a box, is a room here. In my university, there is a detector, Columbia University. It's one of the main experiment of dark matter. Much underground, you have to go take a lift, go there. And then they have to make this whole thing noise-free. Because there is even vibrations can recoil the nucleus. And the interaction rate of dark matter is so low, interaction rate or somehow the probability is so low that with given sigma means the miraculous sigma, okay, which gives the dark matter degree, you expect 1 to 2 hit per year. Okay. So my university graduate students, when they used to work with the same experiment. I used to tell them, what are you doing? Whole year, they say like, we are waiting. Waiting for what? Waiting for WIMP to hit. Because once or 2 times a year they will hit, if they are lucky. And if they hit, if they can prove that it is dark matter, they will get a Nobel Prize. So they waited for 5 years and there is no hit. But they got amazing best PhD award. Why? Because they put a constraint on the cross section. Because if you don't see hit, because you know, given a sigma, you see 2 to 3 hits or 4 hits statistically. If you don't see any hit, that means the sigma is even lower, means the cross section is even less. Then aisa karte, now they continue putting constraint on the sigma, and then this is like the sigma versus the mass of the dark matter, mass of DM. They put a limit and they give a limit. Today, if you see, it's a limit, the upper part is ruled out. So as a karte, then they are going even a much lower limit as you wait and more. So they are almost ruling out. So only now 20% of parameter space is remaining. Baki ruled out. So that's not a very good news for WIMP. Is it clear now? Getting sense? Yes?
Yes, sir.
You understand, no? If their cross section is strong, then they could have, then we know the rate, then we know the number of hit expected. And if we don't hit at all for 10 years, that means the cross section must be low. Clear?
Yes, sir.
And cross section, you cannot just make it low, because if it make you low, then the dark matter density will go high, as I have shown you from freeze out. Yes? Hello? Yes?
Sir, we have a measure of the cross section, right? Like as you mentioned. For WIMP.
Tell me.
We have a measure for the cross section, right? As we measured from WIMP.
No, we don't measure the cross. Yeah, we can if they hit, but if they don't hit, how can you measure the cross section? Okay.
Okay, sir.
So exactly. So we don't know whether. So that's why you have to assume the cross section from WIMP miracle and then see that how much hit you need. So what they do now is, that's what I'm going there. That the rate I told you, rate is 1 or 2 hit or recoil. Hit means recoil per year is actually for 1 kg of nucleus, because you need to know how much nucleus you put. So now what they do, they actually make a bigger thing and they put tons of xenon nucleus, xenon or argon nucleus. Why? Because xenon and argon has a lot of neutron and proton inside it, right? So the more the number of proton and neutron, the more the chance of heat of the dark matter wind with us. Clear? Yes? And this experiment is called Xenon 100. It's the most powerful experiment which almost rule out the maximum parameter space rule out of dark matter. Only little bit left here, I remember. So this is the fate of the WIMP of dark matter. And nowadays, people started thinking, when you look for long time and still it does not work, then you start doubting, right? Yes? So now people have started looking beyond WIMP. I also work on that. That maybe we have just misused our times and billions of dollars for 30 years searching, which means our guesswork, which we did, maybe that is maybe wrong. I'm sorry, it can be. We don't know what it is. We are just, so I give this example. You know the story of Nasiruddin. It's a very deep story. This is his house, and this is a lamppost. Lamppost is like that. Light is coming here. There is jungles here, and one day he lost his key, and Mullah Nasiruddin was looking for his key here under the light, and then he was not finding it. Key finding, okay. And then his friend says, "Are you sure, Mullah, that you lost your key here? You are looking here." Then he said, "No, I lost my key in the house." But then he said, "Why you are not searching there?" Then he said, "No, there is power cut in my house for last 4 days. So there is no light here. There is no light. So I'm searching here because there is light here." You heard this story before?
No.
Yes? Yes or no? How many of you heard this story?
No, sir. I
I
haven't.
do not.
Now it is the time to turn on the video. Okay? Anyway, today is the 11th class. We might meet again, but this class is officially ending. Okay? Other people, our rituals, turning video. Okay? Very nice. Avinash, you are doing good? Yes? Okay, very nice. Shruti, video on. Arpita, video on, but very dark. Is there a cyclone there, Arpita? No, now I can see you. Okay, yes. Srivardhini, is okay if you think about it. We have seen you, so no problem. Okay, but you can turn on the video. So, how many of you heard the story? One. How many of you did not hear the story? This. Okay. So physics, this is what happening maybe. That you can only search things where the light is, because you cannot search where there is no light. Is it clear? Yes? And you have to keep guessing. And if you are lucky, then you will see, wow, I have found. So anything in physics is like that. You assume, and then you build experiment. If you find it, that means your assumption is correct, right? And if you don't find, that means let go the assumptions. Okay, very nice. Now you can switch off the video. Okay. So sometimes I give this joke that it is also a deep story. Mullah did not talk about dark matter when it was coming up. He talked about happiness. That it is nothing wrong to look for happiness, but what is wrong is to look for happiness in something where it is, you know that it is not there. Have you faced that situation? Yes? Yeah? Yes? Sometimes it happens, no? Like you know that it may haini, but still you continue doing it. How many of you agree with me? Yes?
Yes, sir.
Yes. Okay, very nice. So now, let's go back. We are coming to the end. So now we know that what may not be the WIMP. That is the the dark matter might not be the WIMP. We have started doubting it. So what is beyond WIMP? There are two main candidates. One is called PBH, primordial black hole. Another is called axion Boltzmann particle, one axion. Another is some sort of neutrino, not the normal neutrino or sterile neutrino. Normal neutrino, I'll give you an homework. You will do it because I have given all the things needed for that homework. That neutrino decoupling, their number density, how the distribution function does not change. Using that, you will do the homework. I'll give you the homework. Ravi will help you. Ravi, my student, will help you. The homework is, if a neutrino has mass m nu, say 0.1 electron volt, neutrino is very less mass, then find out what will be the omega neutrino dark matter. Neutrino has all the properties of dark matter, okay, today. The answer will be something like m by 100, m electron, if it is in electron volt, times some factor. So if you have 0.1 electron volt, you will see that the fraction will be 0.001. So because 0.1 divided by 100 times a number, you'll get it. So neutrino, but we need for dark matter to be around 0.26 because 26% is the dark matter. So neutrino cannot be the full dark matter. It can be only a sub fraction, normal standard model neutrino. That will be your homework. Okay. So now I'll just discuss PBH a little bit, then we are done. Because this is easy. Primordial black hole. So the black holes are formed when you know that stellar evolution, normal black hole. You know that now? You have done the course, no? How many of you know? Yes or no?
Yes, sir.
Yes, you know. So now I don't have to say. So when the Chandrasekhar mass is reached by accretion, then the white dwarf can form the black hole. Right? Yes?
Yes.
The limit. And the Schwarzschild radius, you know that, no? 2g times m. Yes? Are Schwarzschild of a black hole? Yes?
Yes.
So now, within the Schwarzschild radius, and then the horizon, whatever comes in, you don't see them. Okay? That is the horizon of the black hole. You know that, no?
Yes, sir.
So by the way, just few days back, the astronomers in US, means in South Pole in South America, they just discovered that one star was moving slowly, and black hole, nobody can see them, no? They are like the small, black hole is not that big. You know that the black hole radius is way, way smaller than the sun radius. You know that?
Yes, sir.
How much is a black hole radius per 10 solar mass, approximately? 10 solar mass. This is sun. 10 solar mass black hole. You know what is the radius in kilometer? Who tell? Anybody knows? You don't know?
A few kilometers.
Huh?
A few kilometers, like 10, 20 kilometers.
10 kilometer.
Yes.
Right? So you should know this. You have done so much stellar physics. You know, this is the problem. We understand all the analytical thing, but we don't know the numbers in physics. And the problem is, I have taught in US in many universities. I have done also my master's in IIT. I was almost IIT Kanpur. I was almost topper, Miss Toppery. So I thought I understand mathematics and everything, but when I went to US, I realized that I theoretically calculate everything, but I don't know the numbers. What is the mass? What is this? What is dark matter mass? What is black hole radius? What is the velocity of dark matter? If you don't know the number, you will never get the feeling, right? And for you, physics will remain like, oh, I have to solve that differential. Oh, I have to remember what is the answer. But physics is happening here, right here. If you have a feeling about the number, then only you become a good physics, whatever research you do. So, because when there is numbers, we connect to it with us, isn't it? How many of you agree? Give a thumbs up or something. Yes. So that's why numbers are very important in physics. Otherwise, many a time in our education system, especially in India, you just analytically calculate, but you don't connect it with the reality. And that's why the experimental physics also situation is very bad in India. Okay. Slowly it is rising up. Clear? Yes. So now, what I was talking about, I forgot. Who can remind me? Okay, it is there. My whiteboard will remind me. So M sun. 10 M sun is around 10 kilometers. So can you see that a 10 kilometer object, which is your Pondicherry University campus, can swallow a sun in 2 weeks. So just yesterday, I saw the news came. Someone was talking that, in Corona times, a lot of death is there, but death is there in stellar thing also. One star was moving, and of course it did not know, because nobody knows black hole where it is, and just black hole ate it in 10 days. And when it ate, the black hole is so small, so it created a tunnel thing, and that is called the stellar objects, like a rocket velocity comes in like a huge velocity towards the black hole and cross the horizon, and it eat it. And like a sun mass, like the bigger than sun, it finished it in 10 days. So the astronomers wrote it in Nature article that it was sleeping, and then it became hungry like a tiger and ate a sun. So it's very interesting. Have you heard this news? Yeah. And this news is a little different. It is not a small black hole. For smaller black hole, 10 mass solar black hole, they have seen that it accretes in 10, 12 days. But this was a bigger black hole, and they calculated kind of thing that there is a high chance that it will take longer time, because the radius is much bigger, so it will diffuse and this thing. But actually, it also finished the star in 10, 12 days. And when the stellar mass comes in, it glows because huge energy so enters like a rocket. So you see that like human death happens, the stars also die in the black hole. So black hole is like that, where the information loss happens. Yeah. There is a huge puzzle, no? You know that about the information paradox in black hole? How many of you heard about it? Yes.
Yes.
Yes. That all the things. So for human also like that, no? Somebody is alive doing this, finished, and all information is gone. You are not able to communicate, not able to interact with this. And then but stars also go through that. But for stars, now we know that the information is totally not lost. It's called black hole information, but it goes to a holographic plane and is stored in another plane which you don't see. So who knows? Maybe human death also, after death, the information is stored. In the events of that life or images stay there. Sometimes in other places they talk about it, but it's very similar that whatever is happening in the universe, in the galactic structure, supercluster, and I showed you the brain structure today. And I didn't show you, it is your homework. You see exactly looks like an embodied simulation of dark matter. You have seen, no, filamentary brain structure. How many of you have seen it?
Yes.
It's very similar to the Millennium simulation I showed you today. Okay, very nice. So I tell all these stories because then physics remains interesting, connected with life, isn't it? Otherwise, physics becomes another differential equation, and which is very hard sometimes. How many of you agree with me? Yes? Yes. If you are not motivated from inside, if you are not motivated inspired from this thing, whatever is your mathematical skill, you will not enjoy that much, because not a single discovery happened in physics just because of mathematics. You need intuition, you need realization, you need some deep connection with the nature, you need numbers, you need to feel it in your bone, and then you will feel. Then Einstein said, no, with physics, he could feel that he is merged with the universe and he became free. So that can be also in a way. Is it clear? Yes. So do anything what you love. Otherwise, if you just do it, and love is in every subject. Some people hate physics and some people love physics. So it is the problem with not with the physics, with the person, isn't it? Yes? Agreed. Some people hate geography, some people give their life for geography. So don't say that this astrophysics, I don't like it. It just means you are not going into the depth. Okay? At some point in my life, while doing PhD, I lost interest. Many times people do. But then as I started going deeper, and also started connecting with nature, one of my professor, he was an MIT professor. My first paper is with him. He's not my PhD guide, but he was in MIT. And whomever he will take students, MIT also has an ocean, like your Pondicherry have an ocean. He will say, like, first 5 months, go and sit every day by the ocean, observe the waves, connect with the nature, then I'll give you the problem. You need to honor nature, then only you can do good physics. Getting it? You don't have to sit on Pondicherry beach, but it is there anyway. Do you go there? How many of you go? But because of Corona, you missed the 2 year, almost 1.5 year of your Pondicherry life, isn't it? Yeah?
Yes.
Yes. You should tell university that at least 6 months we should stay. They will give you a chance. Or no? You have to go there, or you can finish your master without going there also. Yes?
Probably without going there.
So you just went in the beginning 6 months, yeah, right?
Yes, sir. That's 6 months.
Okay. But still you can go later as an alumni, no? Yeah. Very nice. So what I was talking, let's go back. PBH. So these are normal black hole, and this black hole also has properties of dark matter, of DM. Why? Because it is only interacting with gravitationally, and it is dark, means it does not emit light, and that's it. It is neutral, or even if it has charge, very tiny charge. But then this PBH, this black hole will not be the usual dark matter. It will be like a normal dark matter, made of visible particle, but black holes. But then we calculated, not me, scientists calculated, and find that rho normal black hole is much less than most of the cases, depending on the mass of the solar mass of the, because different solar mass black holes can be possible, no? 10 solar mass, 50 solar mass. Solar mass is like this dot, 10 solar mass, 50 solar mass. Depending on their solar mass, how much black hole, the number density changes, but most of the cases it is less than 0.26. But we need this omega to be 0.26, or omega, not rho, omega pH to be 0.26. So we know that normal black hole is not dark matter. Mostly. There can be surprise, but that is the idea today. But then there is something called primordial black hole, not formed by stellar evolution. They are formed by something else. They are formed in early universe when there is some density fluctuations. We did the n-body simulation, no, today? N-body simulation, yes? Then, if there is some very high peak in some genus, which is much higher than 10 to the power minus 5, by chance, by some new physics, then when gravity acts on it from early universe, it is shown that they collapse into black hole. You understand, no? that if the peak is low, 10 to the power minus 5, then you don't have enough over density or enough mass. But suppose in a tiny universe is already very dense, that time the peak is very high by chance. Then the density peak means it is in visually, that means you have very high density. And then if you evolve it, it will accrete more mass, just it was doing, and then it will reach the Chandrasekhar limit and it will create black hole. Clear? Yes?
Yes, sir.
These black hole mass are, as it is not stellar black hole, it mass is not, it can be a vast spectrum. You know, for stellar mass black hole, the black hole mass is higher than the mass of the sun, isn't it? Because what is the limit? That Chandrasekhar limit, how much it is, so that it becomes black hole?
Above 1.4.
1.4. So that means if the black hole is formed, you will see that they are more than 1.4, and then they merge or accrete more matter. It will be 10 mass solar mass black hole, 50 solar mass black hole, but you will never get a 0.1 solar mass black hole in stellar evolution, right? Not allowed.
Yes, sir.
But if LIGO, there is a chance actually, people are thinking there is some signal which can be actually solar mass black hole mass less than solar mass, MBH. Then it's a eureka. It will may get another Nobel Prize. Then you will say that, oh, that means in the universe there are black holes which are not from stars dying into black hole, but from early universe, from Big Bang, there is some spike and there is some mechanism to do that. Me and Ravi is also working on such mechanism. There is another paper, 2-3 papers, big short paper, Bernard Carr, whom you read in the book Carr Black Hole. So Bernard Carr wrote another paper long back. So there is a way you can generate that primordial black hole, and they are in very early time. They can be solar mass, they can be even 10 to the power minus 10 solar mass, much lower, or they can be even 10 to the power 10 solar mass, much higher, because there is no stellar evolution needed. And if it is true, and if they form, they have all the properties of dark matter. So who knows that nowadays this gravity wave is going in a very high expectation zone, that not only they may detect gravity wave, they have already got Nobel Prize, they may even detect dark matter if it is primordial black. Okay, so that is one of the main candidates. Okay, so there are many candidates like sterile neutrino or axion that we don't do it here, but that's the end of the cosmology course officially. But you can always ask me questions. Clear? Yes.
Yes.
Yes, sir.
Oh, done. So you have recorded the lectures, Shruti? Where it is? Where do you record? Okay, so can you send me the link also? One or two of my students also wants to see it. Okay. Okay, but I can see, no, if you add me. Okay, but if my students wants to see it, then you have to add him also, no? No, don't make it public, because I don't, because these lectures, no, I don't make it public. Or just one student, I will add you. Only the cosmology video, not the other videos, okay? Okay, yeah, yes. So you can I'll give you the email of that person, okay? You can just add. He's IIA student only, okay, yeah, oh, no problem. Okay, so any more question?
Sir, if primordial black holes are candidates of dark matter, then how can we say about this formation of quarks and all from pair production from them? We can't, or is it like we can assume Hawking radiation and particles will be produced like that?
Yeah, but we don't need quark and all these things, because in this case, it does not, the number density does not happen through that process of WIMP. There is a different way to produce the number density. That WIMP miracle, what I was telling, pair production, quark, anti-quark, electron production, that is only for WIMP mechanism. For PBH, primordial black hole, the number density is calculated from a totally different mechanism. Okay?
Okay, sir. Okay.
It is not. So depending on how you produce dark matter, the number density or the total mass density, total energy density today is calculated. So only for WIMP or any thermal dark matter, thermal means which was in thermal equilibrium early time, then you go through that freeze out. Okay? But primordial black hole is called non-thermal dark matter. Okay? It was not in a thermal freeze out, because once the black hole forms, it is not in thermal equilibrium with the rest of the universe, isn't it? Yes.
Yes, sir.
So it is not. Yes. Good. Any more question about anything? So you enjoyed? Yeah.
Yes, in the diagram before about dark matter, so when we measure for objects, like we said there's a deviation where it doesn't follow 1 by r, but it keeps on following that straight line, and for that we say dark matter. And so when we are measuring things further from galaxy, we are measuring some stars, right? So
no, we are measuring not from stars. The hydrogen clouds are extended. So that HI, hydrogen cloud, they rotate. So there is a way to measure that.
So if those that hydrogen, neutral hydrogen is rotating at that speed, and we have dark matter there, and like you said, this matter is embedded in this dark matter field. So shouldn't dark matter also have similar velocity to the hydrogen cloud?
No, but that hydrogen is in a 2D, because to rotate, you need not only just the initial condition is matter. Whether something having an angular momentum, you see, you can still have a highly gravitational thing which is not rotating. Whether it is rotating or not, it depends on how it is formed initially and whether it has initial velocity, isn't it? Yes.
Yes, sir.
That's the idea. Very nice question. That I can have a very high gravity, but I can still have a stable particle here. But if somebody has given a kick in some early time, then it has to rotate with a high velocity, isn't it, to make the equilibrium, isn't it? Yes. Yeah.
Yes, sir.
So I can still have a particle stable here, because if there is some other attraction here. So there is a way to make the sphere of DM halo stable. That I'm not going to in detail, but you know that it is stable. That means it, but it is not rotating. Like black hole also, no? Black hole can be stable, but not rotating very high speed, isn't it? Yeah. Like that.
Sir, like one more question.
Yeah.
In all the new particles that they find in CERN, are they made of the same fundamental particles? Like, are they like some combinations of the fundamental particles?
Which new particle you are talking about?
So other than like Higgs boson, like they often announce like new discovered particles, right? Like
No. There is
omega
has been come. We have been waiting, but it has not come. Only the Higgs has been a new fundamental particle. But what other particle we are looking for is called supersymmetric particle. Is called mirror particle. Mirror particle. We have not found it yet. Not yet. Not found yet. They will be fundamental particle, but only thing we found is the Higgs. Nothing else. Okay.
So like this WIMP particle.
WIMP we have not detected. WIMP is WIMP will be a new particle. It's called LSP, lighted supersymmetric particle.
Okay.
And we have not detected it.
So it would be a new fundamental particle.
Yes. If we detect WIMP in LHC, Super Switzerland, CERN, it will be a Nobel Prize immediately that year, and it will be also dark matter.
Okay, sir.
Done. Okay, good. So you can email me if you want to understand more. Okay. And go deeper into cosmology or something like that. Okay. Great. Okay. So we can even have one more class before your exam if you have any more clarity to solve when you read the notes. Okay. Good. Yeah. To answer your questions or doubt. Yeah. Your exam will be in July. So in June end or July, June end, we can have one question answer once you read it. Okay. Okay. Good. Okay. See you later.
Thank you so much.
Thank you, sir.
Thank you, sir.